Hello there and welcome back to this video series on control systems. Over the past couple of videos we have been considering second order system, and in specific in the previous video we have considered a second order critically damped system when it is subjected to a step input. After watching this video you should be able to specify the step response of overdamped second order system subjected to step input, and also an approximate response of the same overdamped system. Again, it wouldn't hurt to watch these videos which give overview of Laplace transform. Watch them even if it is more than once, and also these videos 31 to 35, they keep the flavor of the second order system within us. Carefully take notes and solve all the problems mentioned therein, and keep these notes handy. So to begin looking at unit step response for epsilon greater than 1, that is overdamped system, we note that this is the transfer function and this is the Laplace transform of the input. The denominator of this transfer function given here may be written as a product of two terms, s plus s1 and s plus s2. This minus s1 and minus s2 are the roots of this quadratic equation, this equated to 0. We can easily see that s1 and s2 with these values satisfy this expression. You can see s1 plus s2, this is positive, this is negative, they cancel, and you have 2 epsilon omega n. Similarly, s1 s2 is omega n square. So the transfer function can be written as omega n square by s plus s1 multiplied by s plus s2. With this we can write the Laplace transform of output, this whole expression multiplied by 1 over s, and we can split it into partial fractions as given here, a over s plus b over s plus s1 plus c over s plus s2. The math may get slightly messier from here onwards, but that's okay. Life itself can get messier at times. So this is the identity which is true for all values of s. So substitute s is equal to 0, this term and this term, they get cancelled. A times s1 s2, we have seen s1 s2 is omega n square, so a turns out to be 1, and it is a b and c that take messier shapes. Okay, when you substitute s is equal to s minus s1, okay, this term is cancelled, this term is cancelled because s plus s1 is 0, s plus s1 is 0, so you have b times minus s1 multiplied by s2 minus s1 is omega n square. If you simplify a little bit, b takes this kind of formidable form shown here. A similar thing we'll do, s is equal to minus s2, this gets 0, this gets to 0, and you can solve for c. c is obtained like this. So the Laplace transform of the output c of s takes this form. It looks kind of complicated, but it's not really that complicated. It's only the so many square roots that make it appear to be complicated. We take inverse transform of this and we get such an expression. You have s plus something, s plus alpha in the denominator, and so you have e power minus omega n times the same thing multiplied by t. Okay, in the numerator here as well as in the numerator here. If you consider this as term 1 and term 2, look here, this is of the form a plus b, and this is of the form a minus b. A plus b always is greater than a minus b as long as a and b are both positive quantities. So this whole negative exponent is more than this negative exponent. That is one thing we can observe. Second thing, again in the denominator you have a plus b, here it is a minus b. We said a plus b is always greater than a minus b as long as a and b are positive quantities. So you have a bigger negative exponent here and a bigger number in the denominator. Having noticed this, we can say that this term 1 decays much faster than term 2. In fact, if you see in the plot that we're going to show in the next slide, in half a second, this term 1 and term 2, I mean the exact expression and the approximate expression given here, both coincide. Because term 1 decays much faster than term 2, we can omit this and say approximate response is given over here. We will show both this exact response and approximate response in one picture plotted over here. This is the input given, RT, which is unit step input. It stays at 1 all through, and this red one is approximate curve, and this blue one is exact curve. You can see that in under quarter of a second, both of them coincide and they go asymptotically to 1 without exhibiting any oscillations. By the way, this plot is drawn for a system which has omega n is 5 radians per second and the damping ratio is 1.2. In summary, we can say that an overdamped system does not exhibit oscillations. This response is slightly sluggish as compared to a critically damped or an underdamped system, especially in cases where the damping ratio is much greater than 1. The system is really sluggish, okay, but it tracks step input. As time t tends to infinity, we see that either the exact expression or the approximate expression. When t tends to infinity, this negative exponential kills term 1 and it kills term 2 also. So in either case, it follows a it tracks a step input, whether it is exact response or approximate response. I think that's all we have for now. Have a great day.